In Unit 2, Homework 3, we're going to be looking at some basic graphs and looking at transformations of these graphs. So to get started, let's go ahead and look at some parent graphs that we'll be looking at, and you kind of have to know the shapes of these graphs to work the rest of this section. We've looked at a lot of these before. In the top left-hand corner here, we have a constant function. It's the same value of y for any value of x. Over here we have a linear function. This one happens to be a positive slope. We have an absolute value function. A quadratic function is like a parabola. A square root function is increasing, starting at the origin but increasing very slowly. A third degree polynomial goes through the origin along with the third and first quadrants. And now if you add more terms here, like x squared or x cubed plus 2x squared plus 3x plus 1, you'd end up with the extra curve in here that we've talked about before. This is the cubic root, kind of looks like an S shape through the origin. And then we have the reciprocal or the inverse rational function. This is a graph of 1 over x. It's this kind of shape up here in the first quadrant and then the third quadrant. This is an odd function because it's symmetric through the origin. Now notice each one of these functions is referred to as f of x, f of x, f of x. What we're going to do now is we're going to make a list of transformations on f of x. So this could be applied to any of these graphs. Then once we get done with our list of transformations, we'll start applying them to specific graphs that we're going to be looking at. So f of x, transformations. Well, we're going to look at one transformation at a time. So one graph that we could look at is negative f of x. So it would be taking any of these graphs and putting a negative sign out front. Well, the overall effect of this would be to flip the graph across the x-axis. So whatever was above, we flip below, and whatever was below, we flip above. So it reflects itself across the x-axis. So flip the graph across the x-axis. Another way to be to reflect across the x-axis. Okay, another transformation that we could have. Again, I'm back to f of x. Inside the parentheses x, I'm going to put x minus a. Now, this is called the argument of the function. And this is called the argument of the function here. So if you do anything within the argument of the function, it's usually opposite of what you would expect. So for instance, this says minus a, and so you'd think you'd move to the left or down because minus is left or down, but you do the opposite. Because this is within the argument of the function, this is a horizontal shift to the right. And this is what's kind of surprising. It's opposite, a units. So I would pick up the whole graph and I'd move it to the right, however many units we have here. We could also look at y equals f of x plus a. Well, as you might imagine, this is a horizontal shift to the left. Again, it's opposite of what we think because it's within the argument, a units. Okay, we go back to our parent graph, and let's go ahead and look to see what happens if we have, let's say, a 4 out front. And I guess I don't want to be specific. I shouldn't say 4. Let's just say we have an a out front. So if you notice, it's not inside the argument, it's on the outside of the argument. And what this is a vertical stretch, a units. So if this was a number 4, what we would do is we would take the highest point and the lowest point, and we'd stretch the highest point 4 times as many values up, lowest point 4 times as many values down, and that would be my new stretch. So this is a vertical stretch, a units. If this was a was a fraction, and then it would actually be a compression. So we could look at that for our next one. So let's look at y equals 1 over a times f of x. So this would be a vertical compression or squish. So this is a vertical compression, 1 over A units. So this could be 1/2. That would mean I'd take the highest point of the graph and the lowest point of the graph, and I'd stretch it, or sorry, compress it in half as large as it already is. We could also have some values on the outside. So here's f of x. Let's say we have a plus b on the outside. Now this is not within the argument. This is on the outside of the argument, so this does exactly what it says. This would be a vertical shift, and it goes in the same direction as you would think, up b units. Now if we had the same expression with a minus sign, this would be a vertical shift down b units. Okay, so we've covered what an argument is. We've talked about horizontal stretches. We've talked about, actually we haven't talked about horizontal stretches. We've talked about horizontal shifts, right or left. We've talked about vertical shifts, up and down, vertical compressions. So let's go ahead and talk about horizontal compressions now. Now this is within the argument, so again it does the opposite of what you'd think. So what if we had something like an AX in here? It does the opposite. So this is a horizontal, it's within the argument, so this is going to be horizontal. Now it looks like I'm multiplying, let's say by a 4 here, or an integer value. You would think that this would stretch it horizontally, but this is a horizontal compression. It does the opposite because it's within the argument. So this is a horizontal compression by a factor of 1 over A. So if this was 4, we'd take the graph and we'd compress it by a factor of 1/4. Now, on the flip side of this, if we had 1 over A times x, it's going to do just the opposite because it's within the argument of the function. This is a horizontal stretch by a factor of not 1 over A, but basically 1 over 1 over A, which is A. So if this is 1/2, then I would stretch it by a factor of 2, because basically you look at the reciprocal. So those are some of the movements that we can make when we're talking about flipping with the negative on the outside, messing with the argument of a function. It's always opposite of what you think when it's within the argument. And let's look at one more. What if there was a negative inside the argument? Well, when the negative was on the outside, it was a flip across the x-axis. When the negative is on the inside of the argument, would be basically a reflection across, not the x-axis like the other one, but this would be a reflection across the y-axis. So everything that's to the right flips left, and everything that's to the left flips right. So reflection across the y-axis. So what we're going to do is to look at some graphs, and we're going to see what the transformation would be and what they would look like after we took the parent graph and applied these transformations. So to get started, let's go ahead and look at a basic picture of a graph rather than looking at a function. So the graph is trying to explain, in this particular case, what the basic function is. This is a constant function, and it looks like to me my transformation that's taking place up here is f of x minus 2. So g of x equals f of the quantity x minus 2. Now remember, this is within the argument, so I know it's going to be a horizontal. Anything that appears within the argument is a horizontal, either stretch, compression, shift, reflection. So what I want to do here then, horizontal, this will be a shift. Now because it's within the argument, it's opposite of what you think. This is a horizontal shift to the left. Oh wait, not to the left, it's opposite. So we have to go to the right because it's opposite of what we think, 2 units. So every point that we see here, we're going to shift it to the right 2 units. So this point will go to the right 2 units. This point will go to the right 2 units. And this point will go to the right 2 units. So my new graph would look like this. Now in this particular homework set, they give you a list of graphs to choose from. So you would just mark the graph that looked like that. And in this particular case, let's see if I can pop in those alternate graphs. We can see pretty clearly that once we shift those, that it would definitely be letter B in this case. Because all I'm doing is taking the values and I'm shifting them 2 units to the right. It's within the argument, so I do opposite. So that's this graph right here. So I really can't graph these with the calculator because I don't have the original function. So what I need to do is to take a look at the graph and see what they're asking me to do, and then from that graph apply the transformation. Now we have to be careful about which order we apply the transformation in. If there's a reflection, it's usually a good idea to do the reflection last and to do all the other transformations first. So let's look at this example. It's the same graph that we were just looking at. Even goes through y equal 3. But this we have 2 transformations. So let's look at g of x equals f of x minus 3 plus 1. Okay, so we have 2 transformations. First of all, this will be a horizontal transformation because it's within the argument. This one will be a vertical transformation because it's on the outside. This will be a vertical, and because it's on the outside, I do exactly what it says. This will be a vertical shift up 1 unit. This will be a horizontal shift. Now this is a minus 3, so you'd think you'd go to the left, but remember it's opposite of what you think, so we'd go to the right 3 units. So each point I need to do the same thing to. So I need to take this first point over here, I need to shift to the right 3 units, 1, 2, 3, and then I shift up 1 unit. So this point is taken care of. Now this point, I'm going to shift to the right 1, 2, 3, and move up. Sorry, this point right here, I'm going to shift 1, 2, 3, and then shift up 1 unit. So that point is taken care of. This one I'm going to shift to the right 1, 2, 3, and up. And then this is my new graph. Okay, so again, go ahead and apply those transformations. And if you can break it down into the smaller pieces, this isn't too bad. You just have to kind of keep special track to see what's going on there. Let's go ahead and look at another graph on this one. And again, every graph we look at is going to be a little bit different. For this graph, we're going to be looking at a reflection. So let's go ahead and take the graph f of x equals f of negative x and see what we can do with that transformation. So this is this horizontal line, this constant function down here, and so I have y equals f of negative x. Okay, so it's within the argument, so I know it's going to be horizontal. The negative always means reflection, so this will be a reflection across the y-axis. So this is horizontal. This movement is this way and this way. It's a horizontal reflection. So this point will reflect over here. This point will reflect over here, and this point stays right on the axis. So in this particular case with this graph, the graph and its reflection are the same thing. So there's no change that looks like the identical graph after we do the transformation. Now this next problem is where order comes into play. So we need to talk specifically about the ordering here. Now if we do these in the wrong order, we're going to get a different graph. So we have 2 transformations here. We have g of x equals negative f of x minus 2. Okay, so we could do the reflection first and then shift down 2 units, or we could shift down and then do the reflection. Let's do the reflection first. So reflection first. And then second will be this vertical shift down 2 units. And I guess to be more specific up here, this reflection, because it's on the outside, would be a vertical, so this will be a flip across the x-axis. So we flip over the x-axis. Okay, so let's go ahead and do the reflection first. So our first step is reflect over the x-axis. So these points reflect across this x-axis. And then I take each of these points and I move them down 2 units. So 1, 2, down 2, down 2, and then this is my new graph. Now if I had done down 2 units here first and then reflected up, I would have gotten the same graph back. So you can see how important that it is that we follow the directions. Let's do the reflections first and then we'll work from there. Okay, for this next graph we have 3 transformations. I have the negative, the 1/2, and the -3. So let's go ahead and look at those transformations and see how that will affect this graph that I have sketched below. Now if you notice on this one, I'm actually talking about ordered pairs now, not just looking at the graph, but looking at the ordered pairs. So we want to see the overall effect there too. So we have 3 transformations. I have the negative, I have the 1/2, and at the very last thing that I have here, I have the -3. So this is vertical shift down 3 units. It's outside the argument of the function, so it's going to do exactly what you think, this movement down. Okay, this 1/2, it's inside the argument, so this is going to be a horizontal. Now this is going to be the opposite. You'd think a 1/2 would be a compression, but it's actually going to be a stretch because it's the opposites within the argument. So this is a horizontal, a horizontal stretch by a factor of 1 over 1/2 or 2. You take the reciprocal of 1/2 to get 2. And then we also have this reflection. Now this is outside of the argument, so this is a vertical. This is a reflection from up here to down here, so it's a vertical movement. Reflection over the x-axis. So now I have to decide, how am I going to do this, in which order? Let's do the reflection first, then we'll worry about our vertical shift second, and finally we'll worry about this horizontal stretch. Now I could have probably switched the 3 and the 2 steps, but the reflection must come first. I really don't have a choice there. So reflection over the x-axis. So that would mean -3, 1 would become -3, -1. 0, 1 would become 0, -1. So you can see I'm just changing my y values as I flip over the x-axis. And 3, 1 would become 3, -1. So this is that first step. That's the first transformation, is that reflection over the axis. Okay, the next one I decided to do, and again you have to do the reflection first. This says to do a vertical shift down 3 units. Okay, so vertical shift down 3 units. So each of these would go down 3 units. This is the point -3, -1. So it would go -1, -2, -3, -4, down 3 units. Down 3 units, down 3 units. And so this is the graph with the second piece of my transformation made. Now the last one is to stretch everything by a factor of 2 in the horizontal direction. So let's go ahead and look at what we have here. This is the ordered pair 3, -4. This is the ordered pair 0, -4. And this is the ordered pair -3, -4. Well, when we talk about a horizontal stretch, what we do is we take the x values and we multiply them, because that's our horizontal value, is the x. So I take this value of 3 and I double it. 3 times 2 is 6. So I go 3, 4, 5, 6. The x value here is 0. 0 times 3 is 0, so it doesn't move. Negative 3 times 2 is negative 6. And so this is my new graph. So the green represents my transformation. So this is the complete transformation. You have to do the reflection first, and then you can choose how you want to do the other ones, whether you do the horizontal stretch or the vertical shift. It's up to you. But the reflection must come first. Okay, in our next graph, we're finally getting away from that constant function that we've been working with, and we're going to look at a little bit different shape. Now this parent graph isn't like one of the ones that we memorized, but it definitely is a parent graph, and what we need to do is transform it based on what our given values are here. So we have g of x equals f of x plus 2 in parentheses minus 2. So I see two transformations here. I have one that's within the argument, so that's going to be a horizontal. It's going to do the opposite of what we think. So this is a horizontal shift to the left 2 units. Now it's opposite of what you think because it's within the argument. Now over here, this is on the outside of the argument, so this is a vertical, and it's going to do exactly what you think. This is a vertical shift down 2 units. So we're going to take each of the points that we have listed here, and we're going to shift 2 to the left and 2 down to get our graph. So let's go ahead and start here at this point. Let's go shift to the left 2 units, so 1, 2, and then we'll go down 2 units. So there I've taken care of this point. This point, I'll go shift 2 to the left, down 2. This point, 2 to the left, down 2, and I'm right on top of this other point. Up here, 2 to the left, down 2, and I'm done with that point. At this point, 2 to the left and down 2. So some of these have ended up covering the other points that were there, but when you look at this graph, you can see it's exact replica of the blue graph, shifted 2 units to the left and down 2 units. And so the red graph is the transformed graph in this particular case. Now when you're transforming graphs, if it's a horizontal movement, you work with the x values. If it's a vertical movement or stretch, you work with the y values. The next problem, we're going to be looking at a stretch. It's on the outside of the argument, so it's going to be vertical. So let's go ahead and look at the transformations here. So here I have g of x equals 3 times f of x. Okay, this is on the outside of the function. I only have one transformation here. It's on the outside of the function. So this is a vertical stretch. Now, if it's on the inside, it does the opposite of what we think, but if it's on the outside, it does exactly what we think. This is a vertical stretch by a factor of 3. Okay, so what that means is we're going to take each of these. Now remember, vertical means the y values, and multiply times 3. So 0, what I have here for this ordered pair, 0 times 3 is still 0, so this point stays. Now here, negative 1 times 3 is negative 3, so negative 1, negative 2, negative 3. So multiplied by 3. Here, 0, 0, 0 times 3 is still 0, so that stays. 1 times 3 is 3. And then 0 times 0 times 3 is 3. So when I connect these, you can see all I've done is I've taken the maximum and minimum points and kind of just pulled them straight up by a factor of 3. So again, horizontal movement, I work with the x values. Vertical movement, I work with the y values. Now in the next couple graphs we're going to be looking at, we're actually asked to, given a parent function, we're not given a graph, but given this parent function, we're asked to transform it. So for this next one, we'll do some preliminary work, and then we'll pop back into my math lab to actually graph this one. So they're giving us the parent graph of y equal x squared, or f of x equal x squared, and they're asking us to graph g of x equal x squared minus 5. Well, the transformation here then on this outside piece, this is a vertical shift. In this particular case, we're moving down 5 units. We know it's vertical because it's on the outside, and because it's on the outside, it does exactly what we would think. So this is a vertical shift down 5 units of the parent graph. Now the parent graph is basically a parabola that opens up. So we're going to take this graph and we're going to shift it down 5 units. Now we have to be careful of a couple things. First of all, when we shift this down 5 units, it was here from the vertex, I shift it down 5 units. I don't know how wide or narrow it is, so I have to pick one other point, and it doesn't matter what we do. I'm just going to let x equal, let's say, 1. So if x equal 1, I would have 1 squared minus 5. 1 minus 5 is negative 4. So that's the ordered pair 1, negative 4. So I have the vertex that moves down to here, and then I have the ordered pair 1, negative 4. And because it's a parabola, I know I also have this point of symmetry, and I can go ahead and sketch in my graph. And that's what I'm going to be doing in my math lab as well. So let's go ahead and pull in this problem for my math lab. Well, what we'll do is we'll choose the parabola graphing tool, and we'll start with the origin, and then what we want to do is move the vertex down 5 units. So 2, 3, 4, 5. So that's going to be my vertex. Now this other ordered pair, you know, I have to choose another point on this graph. I chose to plug in a 1, and when I plugged in a 1, I have a negative 4. But if you wanted to, you could plug in another value. You could plug in something like a 4. 4 squared is 16. 16 minus 5 is 11, and that's going to be clear up here in this direction. But just choose another point, because you have to have another point to define the width here, and that's my graph now. So when you're using the graphing tools, you always have to have at least one other point other than that nice vertex point that helps me define the movement of the graph. So we'll go ahead and pop this into our notes as well. So one of the key things here is to choose the correct parent graph. So having your list of parent graphs nearby will be really helpful. Okay, let's go ahead and choose another graph from our homework set. Now these next few graphs that we're going to do, I won't formally graph them in my math lab, but we'll just look at some examples of the types of questions that they're going to ask and talk about what the transformations are. So for this next one, they want us to take the graph, our parent graph of f of x equal x squared, and they want us to graph g of x equals x minus 6 quantity squared. So when we look at this, we should be able to glance at these, and then from the glance that we give them, decide what the transformation is, and then graph based on that transformation. Okay. So our original graph was f of x equal x squared. So that's this parent graph right here. This is a parabola that opens up, goes through the origin. If I plug in a point, let's say 2, 2 squared is 4, 1, 2, 3, 4. And this reflects because of symmetry over here. This is my parent graph, and I'm just going to kind of put it in dashed form so we can see what's going to happen here with our transformation. So this is our parent graph. And then from here, let's go ahead and look at our transformation. G of x equals x minus 6 quantity squared. Well, this is within the argument, and because it's within the argument, we know it's going to be horizontal and it's going to be opposite of what we think. This is going to be a horizontal shift to the, now it says left, but remember it's always opposite when it's within the argument. So this is a horizontal shift to the right 6 units. So each one of the points that I already graphed, I'm going to move 6 units to the right. So this point that's at the vertex, I'll move it 6 units to the right. 1, 2, 3, 4, 5, 6. It's right here now. This point that's up here, 4 units, 2, 4, we'll move 6 units to the right. 1, 2, 3, 4, 5, 6. See if we can get it right on there. And this point that's to the left of the axis, now I'm going to move 6 units as well. 1, 2, 3, 4, 5, 6. Now notice I also have symmetry here, and then I can go ahead and draw in my actual graph. I kind of missed that point. Just make it a little bit bigger. But you can see that this graph just shifts over 6 units to the right. So we should be able to glance at a function that's given to us and then talk about the transformations. Let's go ahead and look at another graph. In this particular graph, we're going to have 2 transformations. And again, when you look at these, you want to talk about the transformations first and see if you can kind of verbally list them, and then after you list them, actually graph them. So here is use the transformations of the graph f of x equals x squared. So this is my parent graph. And this is a parabola opening up. Now my transformation graph, g of x equals 1/4 x plus 5 quantity squared, has 2 things going on. We have this plus 5 and this 1/4. Well, the plus 5 is within the parentheses, so we know it's going to be horizontal. This is a horizontal shift to the, you'd think it's to the right, but remember it's opposite when it's within the argument, so it's horizontal shift to the left, and this would be 5 units. Now what about this 1/4? This is a vertical because it's on the outside of the parentheses of the argument. This is a vertical compression because this is a fraction. If it was within the parentheses, we would know it would do opposite because it's on the outside. We know exactly what it does. This is a vertical compression by a factor of 1/4. Now some of these are a little bit hard to graph because that compression by a factor of 1/4, some of those points are a little bit hard to get. So let's go ahead and pull into my math lab here and see what we can get this to look like. So first of all, you draw your parabola tool, and here we are starting at the origin. I want to go 5 units to the left. 1, 2, 3, 4, 5. So there's my vertex. Now because this is a vertical stretch, I work with the y values. The y value here is 0. Now once we click on the graph, this allows me to make some of those changes. So this is a vertical stretch or compression by a factor of 1/4. So I can put in that 1 divided by 4 here. It's not a horizontal stretch or compression, so that factor remains 1. I'm not moving the graph up or down, but I am shifting this horizontally. So my horizontal shift will be not a plus 5 because I want to move in the opposite direction. I'll put a minus 5. Now if you had negative signs running around, you'd put in your reflections, and as soon as I click off of that, it sketches the graph for me. So I guess I didn't need to grab that graphing tool other than to click the original graph, and then it would plot it for me. So we can go ahead and throw this graph into our notes as well. And my math lab kind of gives us a way to work with that transformation, trying to show the horizontal stretch and compression, because it is hard to graph that depending on which factor you're compressing by. So that would be our picture of the graph there. Now this next problem we're going to look at still has the same characteristics of transformations, but the parent graph is different. For this one, our parent graph is f of x equals square root of x. So if you remember the parent graph of f of x equals square root of x, you can look back in your notes, looks something like this. It's not a straight line, it's kind of curved and then kind of plateauing there. Now our transformation has 2 basic characteristics here. The first one I see is on the outside of the argument. This is going to be a vertical stretch by a factor of 4. Now this is within the argument, so it's going to be a horizontal movement. This will be a horizontal shift to the opposite of what you think. You'd think it would be to the left because it's -2, but it's to the right 2 units. So what would happen here, then I would take this graph and I would move it to the right 2 units. And then I would stretch it by a factor of 2. So this value I'd multiply, or sorry, by a factor of 4. This value I'd multiply by 4 this multiplied by 4, and you can see that it all of a sudden becomes very, very steep. Well, let's go ahead and pop this into my math lab so we can get an idea of how to graph one of these. Oh, they asked us just to choose one. So I guess what we did was graph, and we can already see that A looks like the correct choice here. It doesn't let us blow it up too much, but we can see that this is our correct choice. So we'll go ahead and pop this into our lecture notes as well. So just with a basic curve sketch, just that basic shape, we can do a quick transformation and see what these graphs look like. Now I guess one thing I kind of got off track with is we can actually graph these on your graphing calculator as well. For this graph up here, we could have graphed 1/4 x plus 5 quantity squared to get an idea what it looked like in some points. X minus 6 quantity squared, I could graph that. X squared minus 5, I could graph that. It's these types of graphs up here that I can't really graph. So the one that we just did, let's go ahead and look at graphing that with our calculator. So when we're graphing with our calculator, we don't need to worry about the parent function, we just really want to worry about the transformation function. So it's 4 square root x minus 2. So we could go and graph this. Part of my calculator is not showing here. There, now we can see everything. So now I would do 4 square root after you hit y equal. And then within the square root, we would have x, and it was minus 2. Now, if you have a calculator that puts parentheses up, make sure you close your parenthesis and click graph. And we can kind of see a picture there. Now, that looks nothing like the picture we had. The picture we had has a scale of -10 to 10. And I guess, oh, that's right, the last time we used this for a graph, remember we had this x scale was -100 to 100 by 10s. So let's go ahead and change this -10 to 10 so we have the same viewing window, and our graph should look a little more similar. So here we have our -10 to 10. And instead of by a scale of 10, this will just be a scale of 1. And your graph probably already showed that. Mine was just a little bit different because I hadn't updated it yet. So you can see that the graph that we chose in my math lab and the graph that we just graphed on our calculator are very similar. Let's go ahead and do a quick screenshot of our calculator version. And graphing these would be really helpful to check our work to make sure we are choosing the correct graph, especially on a test or a quiz where we only get one chance before we get that counted wrong. And you have to kind of start over with those. So again, it's a good idea to use your calculator to graph some of these. And again, be careful when you're plugging these into your calculator that you have the reflections, the positive and the negative values in parentheses, etc. Now, we've looked at constant functions, kind of like that linear function. We looked at quadratics, the parabolas. We've looked at square roots. Let's go ahead and look at some absolute value graphs now. With this problem with the absolute value, what they do is they give us a list of transformations, and then based on that list, we're supposed to kind of describe what's going on with the graph. So let's go ahead and look at the original function, f of x equals the absolute value of x. Then we'll look at the list of transformations and kind of work from there. So f of x equals the absolute value of x. That's a graph that looks like a sharp V. So this is our parent graph. And if we were just to do a quick sketch of the parent graph, it would look like this sharp V with its vertex piece right here at the origin. So what I have here then for my transformation is g of x equals negative absolute value of x plus 1 minus 3. So I have 3 transformations. So this first transformation is vertical, because it's on the outside of the argument. It's going to be a vertical flip across the x-axis. Now remember, I always do reflections first. So this is a vertical flip across the x-axis. So I have this one. And again, that came from the negative value. I'm going to put a number 1 here so we remember where it came from. Okay, next one, this x plus 1, this is within the argument. So this is a horizontal because it's within the argument. Shift to the, always opposite, it's a plus 1, so to the left, opposite of plus 1 is minus 1, 1 unit. It's always opposite of what we think. We're going to call this number 2. Now let's come over here. This would be a horizontal translation. Translation means picked up and moved, so that would be like the idea of a shift. So this would be marked, and this is for number 2. So translation means shift here. Now our last one here is on the outside of the argument, so this is vertical movement as well. This is a vertical shift down. It's not opposite because it's outside the argument. Vertical shift down 3 units. Okay, so that's a vertical translation, and that is the third one that we've marked here, down 3 units. So they want us to go through, and it says, you know, just looking at this, tell me what transformations are needed. Now the next part to this is it asks me to choose a graph. So let's go ahead and look at what the graph choices are. And then based on these answers from the parent graph, we should be able to pick one out pretty easily. And again, you always start with the idea of that parent graph. I don't know if this will fit on here or not. I'm kind of running out of a page. These aren't too bad. Okay, so we're starting with the parent graph. And remember, we have to do the flip first. So our parent graph is opening up. After we do this reflection first, I should be opening down. So right away I can throw out this graph because it's opening up, and I can throw out this graph because it's opening up. So both of these have that vertical flip. Next, let's go ahead and look at a horizontal shift to the left 1 unit. So if I'm starting at the origin, horizontal shift to the left 1 unit, looks like it would be here. And then I go down 3 units, that would put me right here. So I think my correct graph is this letter B. Over here I shifted to the right and went up. Here I see I need to shift left, go down. So again, you're just basically glancing at these functions and trying to determine what's going on with them. So we've looked at square roots, we've looked at quadratics. Let's go ahead and look at a problem where we're looking at a 3rd degree polynomial next. So here we have this 3rd degree polynomial parent graph. So for the parent graph, this x cubed will basically start looking like this graph going through the origin. Make that point a little bigger. And then it looks like I go 2 units up and 6 units to the left. So we go -6 to the left, 2 units up. Now let's go ahead and graph this one with our calculators to see what we get. So we go y equal, and over here in parentheses, let's clear this out. We have x plus 6 quantity squared. And then we have plus 2. Okay, graph. Now sometimes we'll have to adjust these around. Oh, that's not the right graph. This is x plus 6 quantity cubed. I put squared up here. So let's get a cube up here. That'll make a difference if I can get over there. I'll change that to a cube. Now this will look better. Okay, so there's that shape that we had before, and we can see that it's been shifted definitely to the left and then up also from the origin. So if we wanted to look at this in our parent graph, we could. Actually, let's go here and let's plot the parent graph. So let's hit y equal, let's leave this graph in that we have, and let's just plot x squared. Or sorry, x cubed. I keep thinking x squared. Now if you notice over here, if I go clear to the left, I can change the colors of these graphs. So you see how this is flashing? This graph will be blue, this one will be red. You can also change whether they're dotted or different shapes there. And if I remember, we could change our line to dotted. And I'm just going to do this to do something a little bit different. So there's dotted. And your graph will look a little bit different, I'm sure, kind of depending on what values you choose. But if I graph these on the same set of axes, I can really see this red dots as my parent graph. So this shows nicely my parent graph, and then it also shows that transformation. And those little tiny red dots are actually a little bit hard to see, but you kind of get the idea of that transformation. Now the way that we would work with this in my math lab, let's go ahead and pull in my math lab, is when we graph this, we would grab the tool that's the third degree polynomial, and then I would talk about moving these bars to represent the movement. So this would be a horizontal shift to the left 6 units. So as you can see, these numbers are changing, so I'll go out to -6. And then I have a vertical shift up 2 units. And there's my new graph, and I can check that, and it's good. And let's go ahead and copy that and then compare it to what we got on the calculator. So you can check all of these answers where you're actually given the original function. So you can see that they're very similar, might be slightly different based on scale, but they are very similar. We also have cubic root graphs. I gave you the parent graphs for those at the beginning of this unit. And remember, you can graph all of these, and I encourage you to do that. Now, one problem that you might run into with a cubic root is finding the cubic root function on your calculator. So let's go ahead and look at a cubic root graph and see if we can find that function on our calculator to go ahead and check some work. So here we're going to be looking at the cubic root of -x plus 2. So we have a negative going on in here, so that'll be interesting. Usually our negatives have been on the outside, but this one is on the inside of the function, which means it'll be a horizontal reflection across the y-axis. So our parent graph on this one, this cubic root of x, kind of looks like this flat S shape. Now, the transformations here. I have this shift of 2 units, and I have this reflection. So I have 2 things that I need to work with here. Let's go ahead and grab our calculator, and let's go ahead and graph our parent graph and our transformation graph. I'm going to clear both of these out of here, and let's go ahead and do the parent graph first. That's the cubic root of x. So cubic root, well, depending on your calculator, the cubic root will be in a different spot. If you hit math and you scroll down, if you notice right here, you have that cubic root function. You could also use parentheses and use a 1/3 as your exponent, so that would work as well. But here's the cubic root, and we want just good old x. Now that's going to be the blue graph, and let's go ahead and change that to something different. I guess blue would be fine. Lots of good options here. I just want to find one. Okay, let's go back to the blue. And then those little dotted lines were really hard to see. So let's go ahead and go here and look at a different option. And let's go back to that thicker dot. Click OK. Now I want to go over here to my transformed graph, and let's go ahead and change these while we're here, because remember those little red dots were really hard to see. So let's change these to red, and let's just do a good old solid line here. Now my transform graph was the cubic root, so I'd go to math. Cubic root would be option 4 here. And I'm looking at the cubic root of a -x, not a -x, but I have to use a negative sign, plus 2. Now this one's a little bit tricky. Let's go ahead and graph this. Now remember, our blue graph was our parent graph that you see graphing, and our red graph is our transform graph. So you can see we have this reflection, and then we have, it looks like a shift from this point 2 units to the right. I'm going to change my window just a little bit here. I like my x values, but I want to expand my y values a little bit. I should say zoom in on those y values a little bit, so I'm going to change these from -5 to 5. So there's my parent graph. here's my transform graph. And you can see by changing that scale, they're just not quite as flat and they're a little bit easier to read. Okay, so this is my parent graph in blue, and then my red graph is the transform graph. So this is my parent graph. This is my transform graph. Now when we look at this graph, you can see we had g of x equals the cubic root of negative x plus 2. So because of this negative, we do this reflection, and this is a horizontal. It's within the argument. So this is a reflection or flip across the y-axis. So whatever point was over here moved over here. So this was our point, and it's going to reflect, or it's going to flip direction. So notice that this is moving toward the right, and then we flip it and it's kind of coming down here to the left. And then I have plus 2 within the argument. This is going to be a shift to the right plus 2 units. So this point moved to the right over to here, and then again these points started reflecting across the y-axis. So the step before would be that reflection. So this would be my transform graph. And what you can do in my math lab then in this case is they just ask you to choose which graph represents that. Now the last few types of problems that we're going to see here, because we've looked at a lot of different problems in this homework set, they're going to show you the picture of a graph and its transformation and then ask you to write the function. So here we have a picture of a graph and its transformation. So this is my parent graph. And if we think about that parent graph, this is just y equal x squared. Well, we can see that there's definitely a reflection going on here. So first of all, I see a reflection. So that's going to give me y equal negative x squared to get started. Then I see I have a horizontal movement to the right, 6 units. So horizontal movement or shift to the right, 6 units. Okay, now remember, this will go in the argument of the function, but it's always opposite of what you think. So because we think it's to the right, we're going to write a minus 6 in. So I think that this is probably our answer, y equal negative quantity. And it's important that you have that in parentheses. So we have negative quantity x minus 6 quantity squared. Now the neat thing that we can do here is we can graph this in order to check our answer. So let's go ahead and open up our graphing calculator. Y equal, let's clear both of these out. So this is negative parenthesis x. Now remember, we think it is a minus 6 quantity squared. Let's go ahead and graph that. So it should show up over here. Yep, that looks good. Now our parent graph, if we want to include it, just for a comparison point, we could include that as just x squared in one of these lines. So there's the parent graph, there's our original graph. So that looks like the function that I think was the right function was, because I can compare these now back to my original. Get these on the same graph. So I can see there's my original, there's my parent, and there's my transformed graph, and it matches perfect. So I think this is our correct answer, this y equal negative x plus 6 quantity squared. Notice the negative sign is not in parentheses, it's out front of the parentheses. Now the very last problem in this homework set is a fairly long story problem, But you can read through it, and based on everything that we've been working with and your common sense and then being able to read a graph and definitely be using your calculators to graph these functions and check your work, I think you'll have some luck solving that one fairly easily. As usual, if you have questions about your notes, please bring them to class. We'd be happy to help. You can also stop by the Math Center. Good luck on this assignment.